there is any problem with visibility, or you can't hear me, or I'm planning to use two boards and every now and then I will forget to switch. So just let me know if I make such a mistake, but let me just get rid of this. Okay, so the aim of this course is to present lots and lots of exotic four manifolds, which means we have to develop tools to show that manifolds using different constructions are homeomorphic, but preferably not diffeomorphic. And in the first two lectures, I presented a few examples, and then I also quoted a theorem of Friedman, which tells us that two simply connected smooth four manifolds are homeomorphic if and only if their intersection forms are the same. And the classification of intersection forms tell us that we really have to compare their Euler characteristic, their signature, and the type. The type is a little bit mysterious. On the other hand, it's a 0 or 1 type of invariant, either even or odd. So it's not so hard. If you have sufficiently many examples, then you will have many of the same type, obviously. What I would like to do today is to show or outline or sketch a way to come up with an invariant which is sufficient to distinguish between non-diffeomorphic manifolds. In order to do that, we need invariants, and these will be the so-called Seiberg-Witten invariants. I would like to sketch the definition of the equations today, and hopefully next time I will talk a little more about the invariants themselves. So the idea is very simple. So how can we distinguish two smooth manifolds, x1 and x2? Well, under favorable circumstances, we would like to put a differential equation on both, hopefully the same differential equation in some sense, and then count how many solutions do we have. And then if the number of solutions is different, then somehow the ring of differentiable functions is different, and therefore the smooth structures are different. Of course, it's easy to say, it's much harder to carry it out. The main problem is what differential equations shall we consider? So there is an obvious differential equation for smooth manifolds, namely the D operator, the exterior differentiation, and that's a fantastic candidate, except when you take the solution spaces, they turn out to be topological invariants. So they don't even depend on the homeomorphism type, they depend on the homotopy type of the manifold, so they are not sensitive enough. Then we can consider picking some extra structures, say a metric, and consider the Laplacian, and then take their solution space. Those guys turn out to be too sensitive. They are sensitive for the choice of the metric, so we would like to pick something in between. And historically, the first such operator was discovered or used by Simon Donaldson in the early 1980s. And what I would like to present now is a derivation of that given by Seiberg and Witten around 1994. And then we will see how to apply these differential equations. So the sad news is that in order to set up these equations, we need a lot of preparation. So this is what I would like to do in the first half of this lecture, and then hopefully give you the description of the equations in the second half of today's lecture. So in order to set up things, we need to discuss C structures. And I have to point out that species structures are sort of not so complicated objects, but complicated enough to confuse you. So I would like to start with an easy Lie group theoretic introduction. So let's take n to be at least 3. Of course, 4 dimension will be always 4, but it turns out that 3 and 4 go together in this respect. So I will just focus on n at least 3. And there is a simple implication that the fundamental group of SON, the n by n special orthogonal groups, the group or matrices. So these are orthogonal matrices which determinant 1. This group is actually Z2, or sometimes we write like this. So What I mean by this is that it's a group of two elements, of course, abelian. And here's a little fact about the homology and cohomology of this Lie group. So from that computation, it follows that the first cohomology with Z2 coefficients is Z2, and the second cohomology with Z coefficients is also Z2. So what does this mean in the language of bundles? It just says that there is a unique, non-trivial real line bundle over SON. This line means that there is a unique, non-trivial complex line bundle over SON. So we will somehow consider these line bundles and the corresponding principal bundles, and it will turn out that they will form groups, and these will be our main interest, these groups. So definition, let's spin N be the unique, non-trivial double cover of SON. So this is traditionally called the Nth spin group. And of course, if you just take SON as a topological space, there is a unique double cover of it because the fundamental group is Z2, and this space is that, but we would like to see it as a Lie group. So we have to make sure that it has a Lie group structure. And of course, it can be done by considering this spin N as follows. We are just taking those continuous maps from the interval to SON, which have gamma 0 is the identity matrix. And we consider this set up to homotopies fixing the endpoints. So I just put a tilde there, but what I mean is homotopies fixing the endpoints. And then, of course, we get a map just associating to gamma the other endpoint, gamma of 1, and that will be clearly a double cover because the fundamental group is Z2. So, and now these paths can be multiplied pointwise. So we equip this with a Lie group structure, and that's the spin group. And what is the spin C? Well, now comes the magic, hopefully, if it works. And it almost does. Not exactly. So spin C of N is just spin N cross U1. So the circle group divided by plus or minus 1, 1. So I don't have to explain what do I mean by plus or minus 1 in U1, because it's just a circle. In spin N, the plus 1 and the minus 1 are the two inverse images of the identity matrix from SON. Remember, spin N, SON is 2 to 1. That is the identity matrix here, and plus or minus 1 are the two elements mapping to this identity. Let me know if you can't read what I write. I will try to pay attention to that. Okay. So these are abstract definitions. Let's see what do these really mean in these low dimensions. So I turn the blackboard again. And this is only there are only two prepared blackboards. This is one. So in order to make a little more, these groups to be a little more familiar, I just noticed that SO3 is just RP3. So topologically, it's a fairly friendly space. And spin 3 is the double branched cover, which is just SU2, the 2 by 2 unitary matrices with determinant 1, which happens to be the same as the space of unit quaternions. I really advise you to work out this identity, and it is really modeled on the fact that SO2 is the same as U1. The circle is either SO2 or U1. Well, this is obviously S3, so everything fits. This is really a double cover of SO3, and the double cover map can be given from S3 to SO3 by sending a unit quaternion Q to a map from the imaginary quaternions to itself. Remember, the imaginary quaternions are just three-dimensional Euclidean space by this formula. So it sends H to QHQ inverse. In a very similar manner, or following the definition, spin C3 is just U2, which is nothing as an SU2. Remember that spin 3 across the circle divided by this Z2. And what happens in dimension 4? Well, SO4 is a slightly more complicated group. As a topological space, it's a product of S3 and RP3. The double cover is SU2 cross SU2, which is just S3 cross S3. So the topology is fairly visible. And the map from spin C to SO4 can be given as follows. So remember, the group itself is a product of two SU2s, which are just groups of unit quaternions. So I take two unit quaternions, Q plus and Q minus, and I send it to the map from H to H, from R4 to R4, by sending H to this Q plus H, Q minus inverse. Remember, H is in lowercase h is in boldface H, the vector space of quaternions, which is just R4. And staying in the same spirit, spin C4 can be given by pairs of unitary matrices, A and B, with an extra property that their determinants should be equal. So this is how these guys work out. You have to remember also that the Lie algebra of SO3 is just given by the imaginary quaternions, and the Lie algebra of SO4 as the group on the simply connected level split as a product of two groups is just the imaginary quaternions twice added up with itself. And notice that this is a very peculiar property, because usually the Lie algebra of SON is a simple Lie algebra, except in this single dimension where it is a sum of two other Lie algebras. And we will make use of that fact later on. This will be sort of the source of the equations we will use. So this is one sort of vague philosophical explanation why things are so different in dimension 4 than in any other dimensions. Okay. All right. So it will be important to get representations of these groups. So I will show you a few representations. And once again, I will not use this trick of like prepared blackboards. So what are the representations? Well, from spin C, there are two maps to SU2. Remember, spin C is just SU2 cross SU2, and we can take projection to the first and projection to the second coordinate. So we have the two projections. Likewise, spin C4 as a subgroup of U2 cross U2. It's not equal, but it's a subgroup of U2 cross U2. It has two projection maps to U2, and we can phrase it. Remember, spin C4 is just spin 4 cross U1 divided by Z2. So we can take, as spin 4 is a product of SU2 with SU2, we take two unit quaternions and the unit complex number, and we just associate to one of the unit quaternions and the complex number. And another interesting representation of spin C4 goes to SO3, where this triple, and the bracket symbolizes the fact that we are not taking triples, we are taking equivalence classes of triples since we are factoring out with Z2. And so we send it to the map, which is given here. So Q plus Q minus and lambda sends H to Q plus H, Q plus inverse, or Q minus H, Q minus inverse, depending on whether I take R plus or R minus. And there is a further map. We take the determinant, which goes from spin C4 to U1, where we take this triple and it goes to lambda square. Notice that I cannot write lambda here. I mean, I can, it just doesn't make any sense because these guys are not determined by themselves. They are representing equivalence classes up to plus or minus 1. When we take the square, then this dependence will just disappear. Okay, I should stop every now and then and ask if there are any questions. I see very little feedback from overseas people.
Andres?
Yes?
Would you please mind going back to the representation board for a second? Thank you.
Yeah, I mean, these are formulae and it's good to know them, and we will use probably 2 of these formulae only, but it's sort of helpful to see how these groups are related to each other.
Awesome, thank you.
Okay, so now we go to manifolds. So this was the Lie group prelude, and now we just work with manifolds. So suppose that we have a Riemannian manifold. So suppose that X is smooth. What else do we need? Closed, as always, oriented, equipped with a Riemannian metric. So the principal bundle defining the tangent bundle, so TXX tangent bundle is given by a principal SON bundle, the frame bundle. It makes perfect sense now because of orientation and the metric to consider orthonormal bases which are positively oriented. Principal SON bundle, P SON X. So this is a principal bundle where the fibers look like SONs. They are not SONs because they are like affine SONs. And so here is the definition. And as we discuss the spin groups, I will also talk a little bit about spin structures, although in the lectures, we will only use spin C structures. So a spin structure on X is a principal spin N bundle P spin N X, and the bundle map is denoted by psi, together with a map P spin N to P SON, which I did by rho, which is a bundle map, which is the double cover spin N SON fiber-wise. So what we really have to remember is that there is a spin structure on X is nothing else than a particular bundle, a spin N bundle, which does have some relation to the original frame bundle, namely it looks like this, where this map is just the usual double cover of the fibers. So that's what a spin is. And what's a spin C? And now I might abbreviate a little bit because the spin C will be almost the same. So a spin C structure on X is psi complex spin C at X. So this is a principal spin Cn bundle together with a map which is a bundle map, and we denote it by rho C, which is again fiber-wise.
Andras, there's a question in the audience in the chat.
Okay. Can you read the question, or shall I try to read it?
It's just asking if you can go back to the definition of spin structure, please, for a minute.
Oh, okay. The good thing is that I will repeat this like almost verbatim. So a spin structure is a principal spin bundle which has a very intimate connection to the frame bundle. A spin C structure is a principal spin C bundle, like here, which has a very close connection to the frame bundle. Again, here the request is that fiber-wise, this is the non-trivial complex line bundle, the non-trivial U1 bundle. Question? Yeah, then you will get something else. Okay, so indeed, you can imagine that somehow this is a double cover. This is like a real line bundle over SON, which is the non-trivial line bundle fiber-wise. And this is a complex line bundle or principal bundle of a complex line bundle over PSON. Again, fiber-wise, you have the non-trivial bundle. Okay, so these are the gadgets we would like to work with, and they might not look very friendly. So I will give you a few existence results. So here is a theorem. So X admits a spin structure if and only if the second Stiefel-Whitney class of X vanishes. So I use this terminology of characteristic classes. If you are familiar with it, it helps. If you are not, then you have to remember that there is a cohomological assumption. This class lives in the second cohomology with Z2 coefficients, which gives you an if and only if statement. Moreover, if X admits a spin structure, it admits exactly H1 X Z2 many. Notice that this space parameterizes real line bundles over X. So if you have one spin structure, then for every line bundle you have one. This is not a canonical parameterization. There is a one-to-one map between these guys and the spin structures. And there is a very similar characterization of spin C. X admits a spin C structure if and only if, how did I phrase that? W2 of X is the mod 2 reduction of an element in the second cohomology with integer coefficients. Remember, this is in H upper 2 with Z2 coefficients. And some of these guys are given by taking somebody with integer coefficients and mod to reduce it. Some others might not. X admits a spin C structure if and only if this happens. And if X admits such a structure, then has exactly H upper 2 X Z many. So this space parameterizes complex line bundles. So if X admits a spin C structure, then it admits one for every complex line bundle. Okay, so this is again a general statement, works in every dimension. I saw a question. What was the question? So this is H2. Right? So this parameterizes real line bundles, and this parameterizes complex line bundles. So we upgrade the dimension and we change the coefficient group at the same time. Okay, so let me just clean the board and turn the camera. Yes. And so, so let's see what happens in the dimensions we are really concerned about. So here is the theorem. Any three-manifold admits a spin structure. Well, you know, for me, a manifold is always oriented and smooth. And so if I write Y3, I implicitly assume that it's an oriented three-manifold. So they all admit spin structures, and so spin C. And then we know exactly how many spin and spin C they have, depending on the first and second cohomology with different coefficients. And the reason is that indeed Ty is just the trivial bundle. So every orientable three-manifold or every oriented three-manifold has trivial tangent bundles. So that's not a problem. So when do four manifolds have spin or spin C structures? So here is a condition: X is spin. Then for every alpha in the second homology of X, we have QX alpha alpha even. So the intersection form of the four manifold is even. And this implication holds only if H lower 2 has no two torsion. So this is not an if and only if statement. If the manifold admits a spin structure, then the intersection form is even, and the converse does not hold in general. But if there are no two torsions in the homology, then it does. And
are we assuming like a simply connected four manifolds here or something?
No. So if
no.
if the X is a simply connected four manifold, then this assumption always holds. And for simply connected ones, we have an equivalence. But in general, we don't have that. The torsion comes from H1. So yeah. And X4 always admits a spin C structure. So, you know, informally, you might think that three manifolds are simple because they always get these extra structures. Four manifolds are not that nice because they might not get spin, but spin C is a good substitute for spin. At least every four manifold admits spin C. And then you move on, and not every five manifold admits spin C.
Andres, would you like us to read you questions from the chat?
Yeah, because I cannot.
Yeah, of course. So there's a question from Thomas Kindred asking, should this be for all alpha?
Where is an alpha? Yes.
Rather than there exists.
Oh, yeah, because whenever I write there exists, you should understand that for all and vice versa. No, I'm sorry. Yeah, for all. For all alpha, you know, that's exactly what it means to have an even intersection form. Sorry about that. That would be pretty easy to satisfy, right? You just take, for the existence, you take your random favorite class and you just multiply it by 2. and then it will have an even self-intersection. Okay, so spin C structures are pretty convenient in that dimension because they always, every four manifold admits those. Let me just give you a reason for that, not a proof, but a reason. So let's take this short exact sequence. Here we take multiplication by 2. So the coefficient groups have this short exact sequence, which induces a long exact sequence for cohomologies. And here is a portion of that. So we have the second cohomology of X with Z, and then with Z2 coefficients. Then with Z again, but now the third cohomology. And so here is my W2, which maps to a famous class, which is called the integral third Stiefel-Whitney class, W3 of X. And clearly, this guy is the mod 2 reduction of an element from here, i.e., it's in the image of that map if it's in the kernel of that second one. So having an integral lift of this guy is equivalent to saying that this integral W3 is 0. And here's a fact that Wn-1 of Xn is always 0. So we are sort of in a lucky situation. This holds for in every dimension, and this is a theorem of Stiefel, I don't know, from the 60s. And so it just says that for four manifolds, it passes through, and for other manifolds, we don't. Okay, so we do have spin C structures for four manifolds. Let me just clean the next board.
Andrzej, while you're cleaning the board, just a question about this reverse direction. I feel like I've seen this more with H1 has no two torsion. Am I just misremembering that?
Yeah, and it doesn't matter.
Oh, okay, they're equivalent.
Yeah,
Well,
so
I think
H1,
that just by like Poincare duality,
yeah,
just
so
by like duality, it doesn't like the torsion.
yeah. So the prototype example is actually the Enrique surface. Yeah, which has H1 Enrique Z2, and the intersection form is E8 plus, well, I don't really remember, but something like that. So this is a fantastic and nice even intersection form. It has Z2 first homology, and there is two torsion in the second homology, and then W2 will not be 0. It will be a two torsion class, but not 0.
Thanks.
But isn't just two torsion and one torsion, aren't the torsion in H1 and H2 the same? Isn't that just true by like?
Yeah, so
Basic.
we have to work that out. I will not do that on the board today, but yeah, both conditions are fine. Is it okay?
Thank you.
So now I lost my notes. Yes. So so how do I think about the spin structure in dimension 4? So remember, there is this principal bundle, which is just a principal SU2 cross SU2 bundle. So we can associate to it either using the first or the second projection. We associate to it two quaternionic line bundles over X. So we can think of the spin structure as being two quaternionic line bundles, and then comes this other condition about the relation to the tangent bundle, such that if we take the tensor product of these guys, then we get the tangent bundle. So this reflects that representation, how we go from spin 4 to SO4, if you remember. And this is just the consequence of that. And likewise, spin C in dimension 4 is, once again, we have this this C4 principal bundle. And it's not exactly U2 cross U2, but it's very close to it. It's a subgroup of U2 cross U2. So again, we can take the first or second projection, and this will give us two U2 bundles. And then once again, tracing through the representations, the relation of this bundle with the principal frame bundle tells us that W plus tensor over C, W minus star is the same as the tangent bundle after complexification. So this requires a little bit of a thinking, and we will use that identity over and over again. Okay, so this is how we should think about spin and spin C. They come with certain bundles, and then we can do all kinds of manipulations with the bundles. There is also a geometric representation of spin and spin C, which I will not go into today. And so let me stop here. Any questions? Is there any question in the chat? No. Okay. Unfortunately, I was trying to run the same on my computer, and my computer just shut down, so I don't see the chat. Well, next time I will be a little more prepared. Okay, so let me just continue. Seiberg-Witten equations. So once again, these equations arose in 1994 through the work of Seiberg and Witten when they studied the Donaldson invariants of smooth four manifolds. And I cannot give you a real motivation why they should work. The only motivation I can tell you that they do work and nothing else works. So that justifies me. But of course, maybe we'll understand the true meaning of these equations throughout time, and then we can give a better explanation. But so once again, X4 is a smooth, closed, oriented four manifold. And S is a spin C structure on X, i.e., we have two U2 bundles. And of course, I forgot to mention one condition for these. Let me just get back to there, because you have to remember that spin C4 is a subgroup of U2 cross U2, where we have the condition that the determinant of A is the same as the determinant of B. And determinants can be defined for matrices, but they can be defined for bundles as well. So this identity transforms to the sentence that the two determinant line bundles are isomorphic. Sorry, I forgot to add that. So a spin C structure on X is a pair of bundles which are both U2 bundles, so complex unitary two-plane bundles, together with the identification of their determinants and with an isomorphism like that. Okay, so let's see. We have X and we have a spin C structure where we just simply think of these two given bundles satisfying those properties which I just put up on the board. Let me sort of change this expression . We replace it by the fact that this just means that there is a map gamma from the complexified tangent bundle to this tensor product, which happens to be the same as the space of homomorphisms, complex homomorphisms from W plus to W minus. So using this equivalent formulation of this isomorphism, what we can do is that if we have a section of W plus and the vector field, then I can sort of, the vector field gives us a homomorphism from the sections of this guy to the section of that. I can apply it to the section, so we can go from W plus to W minus using a vector field in Tx. So that's what's called Clifford multiplication. And so that will be very useful in a moment. Let me just free some space. Unfortunately, we have to make a little detour and remind you what connections are. So let me just turn the board. Yes, okay. So recall, if Px is a principal G bundle, where G is just a randomly chosen Lie group. So the fibers all look like G, but they are not canonically isomorphic to G. They are sort of affine Lie groups. Then a connection is a Lie algebra valued one form omega So it's a one form on P on the principal bundle, which means that it associates a value to every tangent vector. So it's really a function on TP. And it's not a random, it's not a real valued function. It's a Lie algebra valued one form. So it maps from TP to the Lie algebra of G. And it has to satisfy the following two conditions. Omega is a fixed isomorphism fiber-wise. And I will explain it a little better. And then it also has another property, which I just write, and then we can forget about that. And I will try to draw. So what is my principal bundle? This is P, and this is my X. And the fiber looks like G. It's not exactly G because we don't know who is the identity element. Once we pick an identity element, it becomes G. G has a free action, which sort of moves inside the fiber. So a tangent space, which is vertical, which is tangent to the fiber, is canonically isomorphic to the Lie algebra. So for my one form, I demand that along the fiber, it should be that fixed isomorphism. What happens in the orthogonal direction? Well, we don't know. So we can take the kernel of this omega, and this will be a direct summand, summoned in the tangent space. And this second condition just tells us how to relate the different such orthogonal direct summands within the fiber. So we can go from one to the other by a group element. And this rule just tells us that the orthogonal, the zero set should go to the zero set. Well, what do we have if we have such a distribution of orthogonal complements? It allows us to lift curves. If we have a curve down here and I prescribe where do I want to start it, then I can continue by demanding that it should be always orthogonal to these horizontal orthogonal complements. So, it will work like covers. So the phrase we could say is that a principal G bundle where the fibers are not discrete anymore, not like in a cover, but we do have a connection, they will suddenly start to behave like covers. It's like a G-fold cover. G is just a Lie group, so there are continuum many leaves, and it's not a complete analogy, but it's sort of good to work with. And this allows us to do covariant differentiation on every associated bundle. So this allows, so how did I formulate that? So a map gamma E to gamma E tensor Tx star for every E associated bundle. So if we fix a connection, then we know how to lift curves. So we have parallel transport. We do have parallel transport for every E, provided we tell a tangential direction. And for some technicalities, I put this over, I put the tangent vector to a cotangent vector there. And so we have this covariant differentiation, which depends on this omega. So this Lie algebra valued one form just does everything for us. Okay, so what happens if we have a spin structure? So remember that a spin structure is just a double cover 2 to 1. So X is a Riemannian manifold. So it comes with a canonical Levi-Civita connection, providing the Levi-Civita connection. So we do have a Lie algebra valued one form on this principal bundle, and we can naturally pull it back. You know, it's just a simple pull back. So we do have a connection on this bundle as well. So this gives us gives a map on the spinor bundles. Right? This is the covariant differentiation, but we do have another map because of the Clifford multiplication we talked earlier. So we have a map like that. So this is Levi-Civita, this is Clifford. And when we put them together, we do have a map which turns sections of one of the spinor bundles to sections of the other. And so, okay, so what happens if we don't have a spin structure? Remember, this started with a spin. So we have to conjugate this idea a little bit when we only have a spin C. I will try to copy that, and then at some point we will get stuck. And then we have to think, and that's always a problem. Okay, so we do the same. So we have the Levi-Civita, which is just a Lie algebra valued one form here. And we would like to pull it back, but that's a problem. So in the spin case, the Lie algebra of SON was the Lie algebra of spin n, but this is not true anymore. This is not equal to the Lie algebra of spin C of n, since the two groups have different dimensions. This is one more dimensional than this guy. Remember, spin Cn is the unique non-trivial S1 bundle over SON. So we need an extra data in order to make a Lie algebra valued one form out of this guy. We also need something which goes to Lie of U1. And if we put them together, then we have a connection on there, and then we just repeat what we said before. Where do we get that? Well, so fix a connection on the determinant line bundle of W plus, which is the same as the determinant line bundle of W minus. And from now on, I will denote it by L. So fix a connection there. This will provide exactly the missing component, put it together with the Levi-Civita, and we get what we had before. So we get a map from the sections of the W plus to here. And once again, Clifford multiplication brings us back there. And then we have a composed map. But notice that it's not God-given. It's not only given by the C structure. We had to fix a connection on the determinant line bundle. Let's call it A, this connection. So this will be an operator, which also depends on this choice A. And this is what we have. Yes. You can pull it back to the spin group and then you will see that. Yeah. Okay, so what do we get? So for a connection A, let's script AL denote the space of U1 connections on L, and for a section psi of W plus, we can write down a very simple equation. Namely, we consider this operator we just got before, which required the choice of a metric, which we always do, the choice of a spin C structure, which we already did, and the choice of A, and we would like to evaluate it on psi. And that's our first equations out of the two Seiberg-Witten equations. And time is pressing a little bit, so I would like to try to write down the second equation as well. And this will require a little observation. And the little observation is the following. So here is how to see a little better the Lie algebra of SON. I claim that it can be identified as a vector space with lambda 2 of Rn. So these are just two forms or on Rn. And then the identification goes in the following way. If we take, so this is just those n by n matrices which satisfy this condition. Right? You have to remember that SON is just those matrices which satisfy A transpose the identity. And if you differentiate that property, then you will get exactly this. So that's my Lie algebra. And so I do the following. So for such an A, I define a two form omega of A on alpha and beta, where the definition of this guy is just the scalar product of alpha with beta. So of course, Lie of spin 4, sorry, Lie of SO4, as discussed, it's just Lie of SO3 plus Lie of SO3. So, which is just im age plus im age. So this, again, this is the only Lie algebra among the SONs which splits as a direct sum. So this shows, this gives a splitting of lambda 2 of R4, right? Since this guy is isomorphic to that, and the corresponding splitting is denoted like this, lambda plus and lambda minus. And let me give you an intrinsic description. So in order to define these two subspaces, I need an operator star, which goes from lambda 2 of R4 to lambda 2 of R4. And I will specify, it's a linear map, so I will specify it only in a basis. And the basis can be written like this. So we take EI wedge EJ, and this element should map into EK wedge EL, provided IJKL is an even permutation. So we define it on a basis, and then lambda plus, and then any element. So how do I define? Omega in lambda 2 can be defined, can be decomposed as a sum if I'm not mistaken, yes. So these are the guys, omega plus star omega will have the property. So it's not very hard to see that star squared is minus the identity. Yes. Or the identity, sorry. And then if you apply star to this guy, it stays itself. And if you apply star to that, then it will go to its negative. So these are the self-dual, the guys which stay the same under star. And these are the guys which pick up a minus sign under star. And the claim is that this also gives you a decomposition of lambda 2, and the two decompositions are the same. And this is the reason we denote it by plus and minus. And my time is almost up. So let me just give you one more map, and then we are done for today. So, so consider the map sigma, which goes from the quaternions to the imaginary quaternions, which does the following. It sends age to minus H I H bar. It's clear how to conjugate a quaternion. And this map is spin C4 equivariant, where spin C acts on H by rho plus and on the imaginary quaternions by R plus. So this is a very specific map which sort of intertwines with an action of spin C4 here and there. Therefore, it also gives a map from gamma of W plus. I also denote it by sigma, or maybe sigma bar, from here to gamma of lambda plus of X, where we use the fact that if you take the principal spin C4 bundle and associate to it with the R plus action, then you exactly get lambda plus. I'm sorry, it's a little bit too fast, but once we have this map, we are now ready to write down the second Seiberg-Witten equation. And this is it. So for A and psi, consider the following. The connection admits a curvature FA, which will be an imaginary value 2 form. which splits as the sum of the positive and the negative part, as we did for the lambda before. And so we can take the projection to the first part. So we get FA plus, which is in here. And for psi, so this works for A. And for psi, we can consider sigma psi, which is in omega plus of x. And putting that two together, we demand the second equation to be like this. Well, this is where I will stop today. It was a long story. It was very complicated, I guess, with a lot of new features. The upshot is that you start with a Riemannian four manifold, you pick a spin C structure, and then a connection on the determinant bundle of these spin C U2 bundles, and the section will give rise to an operator, and we can demand the section to satisfy this equation. And we define this sigma bar map, which takes a section to another section. And the curvature decomposes as a plus and a minus part, exactly because of the splitting of this four-dimensional special orthogonal group. And so we have these two equations, and the claim is that the solution set of these equations will provide very important information about the smooth structure. The problem is that at this moment, it also depends on the choice of a metric. So we have to address these kind of questions, and then we have to discuss how to count solutions. Maybe there are infinitely many solutions, and then there is no way to count them. And indeed, this will be the case. So this is what we will do next time. Are there any questions? Or I killed everybody.
Oh, Andres, I have a question. Can we go back to the definition of sigma bar, the map sigma bar? Because yeah, I did not get it.
Yes, so this is the definition of sigma. This is just on the fibers, and then whenever this is a spin C equivariant map, then it induces a map between the bundles and therefore between the sections of the bundles. Maybe I squashed two steps in one. So this goes to where the fiber is, the role of the fiber is played by H here by the imaginary quaternions. You have an equivariant map, you get a bundle map, and then it induces a map between the sections. Is
Thanks.
that?
Yeah, that's pretty clear. Thanks.
Okay. Any other questions? So if there are no other questions, then I will thank you guys for your attention. So we will go on and talk a little more about the Seiberg-Witten story, but now we have the equations, and then I will indicate again how to apply the constructions to get some interesting information about the smooth structure of the four manifold. And hopefully next time we will present the first pair of exotic four manifolds, exotic pairs, and then I will try to show more and more, like infinitely many homeomorphic but pairwise not diffeomorphic manifolds, and so on. So that's the plan. Okay.
Let's all thank Andras for a wonderful lecture. Okay. So let me stop the recording.